All right, the auto-ionization of water. What does that even mean? That phrase, auto, okay, think about happening automatically, ionization, forming ions of water. In pure water, at room temperature, water will naturally ionize itself. So two waters can get together, and one of them can donate a hydrogen to the other, forming H3O plus and OH minus. Okay, this just naturally happens in a container of water. One of the waters will accept the hydrogen from the other one, leaving H3O plus and OH minus. Now, this happens a very small percentage of the time. So it's not like you've got a huge beaker of H3O plus and OH minus. Okay, we're talking about 1 times 10 to the negative 7th concentration of these things. So the H3O plus concentration will be 1 times 10 to the negative 7th, and the OH concentration will be 1 times 10 to the negative 7th. All right, let's think about that for a second. Those two concentrations in pure water have to be equal, because the only way that H3O plus forms in pure water is to take a hydrogen from another water to form OH minus. So these will be equal in pure water, and the solution will be what we call neutral. Now, if the temperature of the water goes up, okay, this is key, this is not written on your slide. If the temperature of the water goes up, this will happen more often. We will have a higher concentration of the H3O plus and a higher concentration of the OH minus, but they will still be equal. However, this number will change. We use these numbers a lot in our calculation. You're going to see how they create the baseline for our calculation, but they only hold true at room temperature. Right? So we can write an equilibrium expression for this reaction because it is an equilibrium. So we've got our products, H3O plus and OH minus, and their concentrations in brackets, and we would divide by reactants, but the reactants are a pure liquid, so we're leaving those off. We're going to plug in the concentrations of H3O plus and OH minus to find the value for this. So the value for the equilibrium expression for water is 1 times 10 to the negative 14th if we're at 25 degrees Celsius. If the temperature goes up, remember these numbers would go up, but they would both go up by the same amount, and our KW value would then be different. It would be higher as well if the temperature was higher, and vice versa. If the temperature went down, then it would go down, and so would our concentrations. These values for KW, or this value, excuse me, is found on the AP equation sheet. So you don't have to memorize this value, but it is key to note that the H3O plus times the OH minus is equal to this value as long as we're at 25 degrees Celsius. Right? So there's your equation again. This KW expression and its value is going to be key in our calculations. So if we know the concentration of the H3O plus, then we can also know the concentration of the hydroxide minus. Also important to note in this calculation, if we add something to the solution that causes the H3O plus to go up, it will likewise cause the OH minus concentration to go down to maintain this equilibrium in water. We need to memorize, or at least know where it is on the equation sheet, this value. Okay, it's going to come in handy as we go through. All right, here's an example problem. The concentration of hydroxide is found to be 1.4 times 10 to the negative 11th molarity. Find the H3O plus concentration. So we have the OH, we're looking for the H3O plus. We're at 25 degrees Celsius, so we know our Kw value. So we're just trying to solve for H3O+. So from the previous slide, we know that the Kw equals the H3O+ concentration times the OH- concentration. We can then rearrange to solve for H3O+. We know Kw, this value is a constant unless the temperature changes, and we know OH-. So we plug in and find that H3O+ equals 7.1 times 10 to the negative 4. Notice that the H3O+ in this case is greater than the OH-. So we do not have a neutral solution. If your H3O+ concentration is greater than your OH- concentration, you have an acidic solution. All right. H plus versus H3O plus. This is kind of a side note, but we'll run into this a lot as we go through. Acid-base equations can be written including water, as you see in the first example, where we would form H3O plus, or in sort of a shorthand way, we can leave out the water and just write H plus ions. They mean the same thing. So this is the key note here. Whenever you see H plus or H3O plus, we're talking about the same thing. So don't let that confuse you. Some of you may write water in some of your reactions, and some of you may write it in others or not write it in all of them, etc. They are the same thing. So don't get caught up on that distinction. All right. Calculation time. pH. pH. This is derived from the French term that I cannot pronounce, but it means power of hydrogen. And this was developed actually by someone in a Coke bottling plant, and they had to check the hydrogen ion concentration in the solutions to make sure they were being made correctly. And it was such a big or small number each time that he needed a way to simplify it, really. And so he came up with this pH. The pH expresses the negative power of 10 for the concentration of H+. For example, if you have a solution and it has a concentration of H3O+ or H+ at 10 to the negative 4, then the pH would be 4. Okay, it's telling you the negative power of 10. If you had a H+ concentration of 10 molar, that's 10 to the first, right? So your pH would be -1. So it's telling you the negative exponent on the H+ concentration, but if it's a positive, then it would be a negative. The reason that we do that is because concentrations are almost always less than 1. So we usually have a negative exponent. So instead of having negative pHs, it's telling us the negative power. We get rid of the negative. All right. For example, if we want to find the pH of pure water at 25 degrees Celsius, we need to know the H+ concentration, or the H3O+ concentration. So we already know that Kw equals OH- times H+. And we know that in pure water, those two are equal. So we can say they're both X. So we could do X squared, okay, to find these concentrations. So we already know, actually, from a previous slide, that in pure water, these concentrations are 1 times 10 to the negative 7. So therefore, the pH, which just tells us that negative power on the 10, is 7 in that neutral solution. All right, what if the solution, though, has a pH of 5.63? That's not a really pretty number, right? We want to find the H+ concentration. Right, the pH tells us the negative exponent on the scientific notation. So therefore, if we're looking for the H+ concentration, it is 10 to the negative 5.63. Now, I don't know what that is, but my calculator does. So I'm going to put in my calculator 10 to the negative 5.63, and it's going to tell me, that the H plus concentration is 2.3 times 10 to the negative 6. Notice that I don't just have a pretty 10 to the negative number anymore, but this exponent is very close to my pH. And then I have some number here to balance out the fact that it wasn't a whole number on my exponent. Alright, so what equations do we need? We need to know that the H plus concentration is equal to 10 to the negative pH. This equation is used to find the H plus or the H3O plus concentration. However, if you know the H plus or the H3O plus and you're trying to find the pH, then you would use this equation. pH equals negative log, that's how you get the exponent out of 10, is to do the log, and we're doing the negative because it's the negative pH. So negative log base 10, which is what your calculator naturally calculates in, of the H plus or the H3O plus concentration. For example, if we have pure water, we know the H3O plus is 10 to the negative 7. So we do negative log of 10 to the negative 7. The log is negative 7, and then the negative log of the negative makes it just 7 for the pH of pure water. Right, this is the pH scale, and it is again based from pure water, because in pure water we know that the H plus and the OH minus concentration have an exponent of 7. So that's where this 7 scale came from. And we know that the KW value is 10 to the negative 14. So that's where this 14 came from. You can have negative pHs. You can have pHs less than 1. You can have pHs above 14. Okay, they're rare, so this is the most common scale. And you can see some of the items listed on the scale. You have hydrochloric acid down here at the bottom, lemon juice at 2, okay, very acidic, vinegar and soda pop also pretty low, this can eat your teeth away, tomatoes moving up, coffee still acidic, water at 7. Our oceans are somewhat basic, cleaner, ammonia pretty basic up here at 12, and then sodium hydroxide even higher up at 14. So if we are less than 7, we consider the solution to be acidic, and greater than 7, we consider it to be basic. Now, if the temperature changes, so we're not at 25 degrees Celsius, which is where this scale is based, then the scale is going to shift a little bit. So neutral will no longer be 7 if the temperature changes. It'll be close, but it'll shift up and down depending on the temperature change. Because remember, the temperature change will affect your H plus and your OH minus, and that will therefore affect your pH. Alright, let's look at an example of calculating the pH of a strong acid solution. And this is key because this method is for finding the pH of a strong acid solution and will not be effective if we have a weak acid solution. In this example, we're asked to find the pH of a 2.5 molar hydrochloric acid solution. We know that hydrochloric acid is a strong acid because remember, chlorine has a fairly large radius, so that hydrogen can break off from the chlorine easily and move into the solution. The molarity of the whole solution is 2.5. And if we think about HCl, if it's a strong acid, it's going to completely dissociate. So for every HCl that you had before, you now have one H plus and one Cl minus. So if the concentration of the whole thing was 2.5 molarity, then that is the concentration of the H plus and the chlorine minus now, right? If you had 2 of them, you have 2 of each. If you had 17 of them, you have 17 of each. If you had 2.5 concentration, you have 2.5 concentration of each. So when we look at our equation for pH, it says to take the negative log of the H plus concentration. So we can assume for a strong acid that this concentration is the H plus concentration. So we just plug it in to our calculator. Negative log of 2.5 equals negative 0.40. Now, a note about sig figs. The number of significant figures in the concentration is equal to the number of decimal places, not sig figs, but decimal places in the pH. So weird sig fig rule about pH because it deals with logs. However many sig figs you have, that's how many decimal places you need in your pH. All right, another example. Calculate the pH of a 0.05 molar H2SO4 solution. All right, well that is what kind of acid? Strong acid. And even though it has two hydrogens, it is only the loss of the first hydrogen that is significant. Acids lose one hydrogen at a time, and as they lose hydrogens, they get weaker. So it loses this hydrogen completely, and then it forms a weak acid, which will lose some of that second hydrogen, but not as much, not completely like the first. So we're just going to use the molarity that they gave us and assume that it only lost one hydrogen. So the pH is the negative log of that concentration they gave us, and then that tells us a pH. Now if you look at your sig figs, this only has one sig fig, so we're going to answer to 1 decimal place in our pH. All right, here is another example. Here we have a solution that contains 2 strong acids. So we want to find the pH of a solution that has 500 milliliters of one strong acid and 250 milliliters of the other strong acid. And we want to assume the volumes are additive. So we want to assume that now we have 750 milliliters. So the first thing we need to do is to find the final concentration of the H3O+. Now, I want to make a note here. If you are mixing a strong acid and a weak acid, you can basically ignore the weak acid because its contribution to the pH is minimal. But if you are mixing 2 strong acids, or 2 strong bases for that matter, you need to consider both of them because they are both contributing to the pH of the solution. So first off, we need to figure out how many H plus ions we're getting from HBr and how many we're getting from HNO3 in terms of moles. So we do 0.15 times 0.5 for HBr and 0.25 times 0.2 for HNO3. So we're multiplying our molarity times our liters to find our moles. So now we know how many moles of both of them we have. And we know they both are going to completely donate one hydrogen. So we can say that that is also the moles of hydrogen, and we can add those together. We then can divide by our liters to find our molarity. So we have moles from the HBr, moles from the HNO3, those are going to be additive. We have liters from both, which we're going to add together and divide, and then we have our molarity. Once we have our molarity, how do we find the pH? We simply take the negative log of the H plus concentration. The negative log of that 0.17 gives us 0.77 for our pH. Now let's note that we had 2 sig figs in our concentrations. So that's why we have 2 sig figs in this final concentration, and therefore 2 decimal places in our pH. All right, we are close to the 20-minute mark, but I just have a couple of slides left, so I want to finish this section. On this slide, it talks about the H plus that occurs from the auto dissociation or auto ionization of water. Remember we talked about earlier that water auto ionizes to produce its own H3O plus and OH minus. And we said that when it does that, this would be the concentration of the H3O plus. However, that is not important in anything other than pure water. So if there is anything else in there other than pure water, that amount of H plus that's formed from the water is not important when finding pH. Okay, I'm not saying that it's not important overall, but if you're trying to find the pH, you need to focus on what was put into the water, not the fact that there was some H plus in there when the water was added. Because 1 times 10 to the negative 7 is a very small number. It's not going to affect your pH that much if you have something else in the water. And also, if you add something to the water, H plus or OH minus, it is going to shift the equilibrium of the water back to the left, thus decreasing that even further. So, the auto ionization amount is insignificant unless that's all you have in there is water. All right. One more formula to add before we go for today, and that is the POH, and it is exactly the same as pH. We just inserted OH. So POH equals the negative log base 10 of the OH concentration. All right, so if you have a 1.5 molar KOH strong base, again, this only works for strong bases and strong acids, and you want to find the POH, well, you have a 1.5 molar OH solution, right? Because KOH has one OH in it. So we can just assume that we completely break down KOH. So our concentration of OH is also 1.5. Negative log that, and you found the POH of negative 0.18. We'll talk about the relationship between POH and pH later, but for now, make sure you know how to find pH, how to find H+, how to find H3O+, and how to find POH.